Okay, so this talk is about closure of orbits of mapping class group in character varieties. Let me start by defining some of these words. So in this talk, sigma sub g comma n denotes a surface of genus G with n punctures or marked points or n holes. So you can see it like this picture over here. So the usual picture of surface is usually like this, but I like it a bit less because it's not clear that the handles are in fact symmetric. So there is no difference between this one and the middle one. There is no middle one. So it's easier to see that they are all the same by having a sphere and then attaching handle to all of them. Then you can see that there is no difference between, there is no middle one. So you put them around this and then you put the holes after that. Then it's known that if I go through these loops, the yellow ones, and then the red ones, and the yellow one, the red one, and so on. And then, so if I do the commutator of A1 and B1, A1 and B1 inverse with this ordering, it will be the necklace of the first handle. So the commutator of A2 and B2 inverse would be the necklace of the next handle. So if I go through the necklaces, and then through CIs, I can contract it from the back of the sphere. So through these generators, we do get this well-known relation of the fundamental group. So the fundamental group of this with respect to the marked point in the middle. And I'm going to denote this with this. And so this group is isomorphic to a fundamental group of the surface. And it's given by the generators A1, B1, AG, BG, and C1, Cn. And the relation is given by, okay, so the way that I drew the curves, I need to put inverses for B1s, but there is no difference. As a group structure, they are the same. So just be compatible with the curves that I have over there. So this is the relation. So it's well known that the fundamental group of this surface is isomorphic to this. Now, we can define representation variety of any group, and that's rather easy. So what is it? So first, I'm going to treat it as a kind of a functor. So I give it a unital commutative ring, and it spells out a set. And because I can identify this only by these two pair of numbers, I'm going to write it as rep G comma n, and it's a functor. Again, I give it a ring, and what it gives me is the set of homomorphisms from the pi from this group to, and here I'm focusing on SL2 representation variety. So it's just SL2 of R, and of course this had been studied and had been worked out for other reductive groups, but for the purposes of this talk, I am focusing on SL2 representations. Okay, so, and whenever this group is a finitely generated, you can define it for any group. So whenever it's a finitely generated group, this functor is in fact is a representable functor, and you can view it as a scheme. So this is a scheme, is a closed subscheme. So this can be viewed. So in order to understand the homomorphism over here, I need to give you 2G plus n 2x2 matrices, and they need to satisfy this relation. So I'm giving you a polynomial relation that needs to be satisfied in order to be inside this set. So that's why you can identify this with a closed subscheme. So I can embed this into copies of SL2 raised to power 2G plus n. So it's a closed subscheme of this. And clearly it's defined over Z. I mean, these relations are polynomials with coefficients inside Z. So this gives me a representable functor from unital commutative rings to sets. Now, what we want to do is kind of think about these representations up to conjugation. That is what we would like to do. And if I conjugate, I'm not changing traces. So what what Friquet observed, and then Horowitz worked out the details for in order to define a scheme over Z, which is going to kind of coarsely parameterize representations up to conjugation. So what Horowitz did, he said, okay, so let's, for every finitely generated group, in my case, it's going to be this group. He said, okay, so let's look at this ring. To every element of this group, I'm going to assign some variable. So I'm going to start with an infinitely generated ring. So to every element of that group, I'm going to assign a variable. So gamma belongs to this. Okay, maybe I define it, call it, I don't know, gamma is fine. So inside the group. And then he used the Friquet relations as the relations that they have to satisfy. Let me quickly point out that by Cayley-Hamilton, if I give you a 2x2 matrix, then trace of x, then I know that x squared minus trace of x times x plus 1 is 0. Now you can multiply both sides by x inverse, so you get x plus x inverse is trace of x. Now you multiply by y, you take trace of both sides. So this is one of the Friquet relations. So this means that if I want to view these variables as traces of 2x2 matrices, then they need to satisfy these relations. So T sub AB plus T sub A inverse B minus T sub A, T sub B needs to be 0. And if I take trace of both sides of this, I get that trace of x squared needs to be plus 2, then needs to be trace of x squared. So I get that T sub A squared plus 2 minus T sub A squared needs to be in the kernel, no matter what elements I pick from the group. And of course, again, you can do this for any group. It doesn't have to be this group that we are choosing. And let's call this ring A sub G comma N. A priori, this is an infinitely generated ring. But what Horowitz showed is that using these relations, this is indeed a finitely generated ring. So Horowitz showed that this is generated so I put a bar over there to emphasize that I'm looking at the coset represented by these variables. T sub omegas, as omega where omega is SI1, SI2, SIK, where S sub j's, A sub ij's are coming from this ordered set of generators. And I'm assuming that S sub I is less than S sub j if I is less than j. So in particular, there are only finitely many of these words that you need in order to generate this algebra. Now that it's a finitely generated algebra, it gives me a scheme. So I look at the scheme that it gives me, and we call that the SL2 character variety of this surface. So I'm going to denote that by CH, G comma N. So this is the spec of this ring. So again, this is a scheme over Z. And we have a morphism from the representation variety to the character variety. And that's, so in order to understand this, I have to give you a ring homomorphism from the ring of coordinate ring of this. So I have to switch from the coordinate ring of this one to the coordinate ring of that one. And that essentially sending it to the trace of rho. Okay, so
maybe a stupid question, but do you assume that T1 equals 1?
Do I assume that?
T1 is I mean the unit in this.
No. So you from these relations, you end up getting that T sub 1 is in fact 2, like trace of identity.
Two. Sorry, yeah.
No, you get it out of the relation.
Okay, thank you.
Yes, so you obtain it out of the relation because this is supposed to be for every A and B. Yeah, you get it that T sub 1 is 2. Okay, so this is essentially this morphism at the level of R points is exactly this, that if I pick, if rho belongs to the R points here, then I'm going to denote the image of this by this one, and that is essentially a trace of rho. So if I take trace of rho of the elements, it gives me the element inside this one. Because again, if I want to describe an element here, I have to tell you what these regular functions do to the element, and T sub gamma of parentheses rho is trace of, so T sub gamma of bracket rho is trace of rho of gamma. That is how you get bracket rho, or you define the morphism. Okay, so now one of the things that people work out at the level of the schemes is to detect whether or not a representation. So I have this representation here. I look at it on the other side, and the question is this information enough to understand my representation is completely, is absolutely irreducible? And they worked it out, and they realized that it's important to look at the so-called the discriminant of every two element of the group. And that is, so one way of saying it is the trace of the commutator minus 2. So if think about it like this, that if this representation was upper triangular, so it was not irreducible, it was an upper triangular representation, then the commutator would have 1 on the diagonal, so the trace should be 2, so this thing should be 0. So we want to avoid this. So, and one computation is actually useful to have is that T, so and let's have it over here because I'm going to use it later. So the T of commutator, if you use the free K relations as we have it over there, the relations between the indices, you can work it out and you see that it is T sub A squared plus T sub B squared plus T sub AB squared minus T sub A times T sub B times T sub AB minus 2. Okay, so you can work it out and you get that it is that quantity. Now you take these discriminants and look at the ideal generated by all these discriminants and look at the set of divisors of that. And we call that one we call this, which is a closed subset, which is a closed subset of the character variety. We call it D sub Gn, and I'm going to denote the difference by C sub Gn cross, subcross. So this is this open Zariski open subscheme of the character variety. And I look at the pre-match of this divisor and then subtract it from the representation variety and denote that by this. So I'm going to give you a feeling about these schemes because at the end of the day, we would like to get an understanding of the R points of these schemes. So I give you some sort of description of the R points of these schemes. Okay, so here is a description. So let's call it a proposition. So we start with this one, and then we look at what it does to the morphism. So if I give you a representation rho here, so a representation rho belongs here if and only if it is absolutely reducible, in the sense that the span of the image of rho is the entire 2 by 2 matrices in the ring R. So for any unital commutative ring, rho belongs here if and only if the span, the R span of the image of rho is the 2 by 2 matrices in R. Okay, so now this gives us a good understanding of the R points of this. Let's see how it behaves with respect to the map that we have over here to the morphism. So let's call it a lemma. So if I give you two representations, and suppose that they end up giving me the same points in the character variety, what happens? I mean, under what condition do we have this? So this happens if and only if there exists an integral extension of R. So this happens if and only if there exists S over R, its integral, and an element G inside GL2S with the following properties. So first of all, this ring S is not huge. It can be embedded into the 2 by 2 matrices with coefficients inside R. And second, this G is not very obscure in the sense that G squared is some constant times G prime, where C is a unit inside S, and G prime is in fact inside GL2 of R. So S is not far from R, and this G is not far from that. And moreover, if I pick any entry of G and any entry of its inverse and multiply them, this product is still inside R. Okay, so it's not far from, again, inner conjugation. And so we have this, and then what? And rho 2 is conjugation by G. So they are not the same, they are not differ by an inner automorphism within the ring R, but if you enlarge the ring a little bit, then they are in fact conjugate of each other. So in particular, if I look at an element gamma and I tell you that rho 1 of gamma is plus minus 1, then rho 2 of gamma is plus minus 1. So this means that within, so that at the level of character variety, already I understand if some of these things are going to center or not. Okay, so at the level of that, of course, I knew the traces as well. So if I just look at the boundary curves, now I understand that the subset goes to plus minus 1 is a property of the points in the character variety, and I don't need to go to the representation variety to understand it, as long as I am in the irreducible ones. Okay. Okay, so R is any unital commutative ring. Any unital commutative ring, yes. Okay, now if I impose condition on R and say that R is a UFD, or I impose condition, I say that every finitely generated projective module is free, like a local ring, then I can drop S and I can just work with R. I don't need to go larger than R. So let's write this as a comment over here. Moreover, if R is a UFD, or let's say a local ring, then S can be chosen to be R. In that case, R1 and R2, so the fibers only differ by conjugation inside GL2R. Okay, but it is important to notice that I cannot, so if I want to understand points inside this, and I look at the pre-image of those, so it doesn't, I mean, this is not necessarily surjective. So as a good example, which people had studied long ago, is the R points of the character variety. So the R points of the character variety in fact consists of two different manifolds. So some of them are coming from the R points of the representation variety, which means you have a representation to SL to R and then taking the trace of that. So some part is coming from that. But some part are coming from the unitary representations. So if I start with those representations from the fundamental group to SU2, then it is inside the complex points, but the traces are always real. And because I want to make it completely irreducible, so I'm going to, it's the same as saying that it is in fact dense. Okay, but let's say completely irreducible. Why should I put this? Completely irreducible. Or, yeah, absolutely irreducible. So the real points consist of two subsets, some part, and in fact, the Teichmüller space is a subset of this part. So what did they do? Is a subset of this one. So when you are taking proper representations of the pi into SL2R, so that would be a subset of this one, and because we are in the character variety, in fact, that can be identified with the Teichmüller space of the surface. Okay, so now I said that we do need to go to some larger ring, but not always. So if I look at a DVR, a compact DVR, then I do not need to go to a larger ring. So let me make sure that I'm covering whatever I want. Okay, so in fact, okay, so let's first understand it in the more general setting. So if I give you a point inside the R points of the character variety, but among the absolutely irreducible ones, again, capital R is any unital commutative ring, then there exists a faithfully flat extension of R such that, and the representation rho inside this larger ring such that X is bracket rho. Now, if moreover I assume R is a local ring, then S is more manageable. S can be isomorphic to something like this, kind of a degree 2 extension for some R. And moreover, if R is a compact DVR, like ZP, periodic integers, and the characteristic of the residual field is not 2, then I do not need to go larger. S can be chosen to be R. So in the case of compact DVRs, so the morphism pi is in fact surjective from the D points of the cross representation variety to the D points of the character variety. And similarly for quotients of that. So let's have it here as another proposition. So again, D is a DVR, compact DVR, and characteristic of the residue field is not 2. So then these maps are surjective. So this one and this is surjective. This one is surjective. So A is an ideal is a non-zero ideal. I don't need to impose the non-zero, and we go via the quotient map. This is surjective, and this one is surjective. So all of them are surjective. I can lift a representation from here to a representation to the D, and the same for the character variety. And as we have described, we also understand the fibers over each point here. Every fiber consists of a single GL2D orbit. For every X here, the fiber is a single GL2D orbit. Okay. Now, one thing that I wanted to mention, but I forgot, so let me mention it now. In order to actually have a formula, at least kind of perspective on what kind of character varieties we are dealing with, let's also mention this example. That the character variety of 1, 1, when I have a torus, one puncture torus, then in that case, it is generated, the pi 1 is generated by only A1 and B1. I don't need the C1 because it comes out of the relation. So I have two generators, and then therefore Horowitz tell us that I only need T sub A, T sub B, and T sub AB. And in fact, they have no extra relations, and this is in fact isomorphic via that isomorphism to the affine space as a scheme over Z. So it's a spec. And the isomorphism, I'm also giving you the isomorphism. So it's just an affine space. But one should be careful. It's not always affine space. If I look at 4-punctured sphere, then it's not as affine space. In fact, so this time again, if I look at what Horowitz says this time I have 3 generators, because the last one is in terms of the first one. And then let's call them C1, C2, C3. So we do know that this thing is supposed to be generated. So it's a spec of, it's supposed to be generated by TC1, TC2, TC3, TC1, C2, TC1, C3. Let me continue here. So TC2, C3, and TC1, C2, C3. It should be generated by these. Now, they do have a relation. So I'm going to write down the relation that they satisfy over there. But one comment that I want to make is that this T sub C1, C2, C3 is just T sub C4. Remember, C4 is that this thing is inverse and the trace doesn't change by inversing the 2-by-2 case. So they satisfy this relation. So if I call this one, okay, so in order to be consistent with my notes, so let's call this one X. It's missing C1, I call it X. It's missing C2, I call it Y. It's missing C3, I call it Z. Okay, so then they satisfy this relation, X squared plus Y squared plus Z squared plus XYZ. It's equal to a linear relation. So W sub X times X, W sub Y times Y, W sub Z times Z plus W sub 4 equal to 0. And what are WIs? So WX, and so why did I put them beside? Because as we will learn later, the T sub CIs are going to play constant for us. I'm going to use mapping class group act on this variety, and the mapping class group is not going to change the T sub CIs. So that's why I'm going to treat them as constants throughout this talk. So that's why these WXs are going to be functions of only T sub CI. So WX is T sub C1, T sub C4, plus T sub C2, T sub 3, C sub 3. WY is T sub C2, T sub C4, plus T sub C1, T sub C3. W sub Z is T sub C, 3, T sub C4, T sub C1, T sub C2, and W sub 4 is the summation of T sub Ci's squared plus the product of T sub Ci's minus 4. Okay, so it's some polynomials in terms of only traces of the boundaries. So that's what you have to remember. The formula is not that important. So here, this means that if I have in mind that T sub Ci's are supposed to be constants, this is the relations that needs to be satisfied by X, Y, and Z. Okay, so now that at least we have seen two of these as character varieties, let's continue. So maybe it's a good place to, in fact, introduce what is a mapping class group, and then what action I'm dealing with. Three-hole sphere is so it's again, okay, so what is it? It's generated only by A and B. So and then I have say it again. C1, C2, yeah, right? Yeah, yes, you're right. Consistent. So C1, C2, then it should be T sub C1, T sub. So it's again ring of polynomials. In that case, it's affine space. And it is consistent with the Teichmuller theory, right? So there, if I want to give you just the pants, I need to give you what are the length of the curves, then that uniquely determines what is the hyperbolic structure inside. So it's the same picture. Okay. Okay, so now what is a mapping class group? So mapping class group you can define for any manifold. You look at all the diffeomorphisms of the manifold, but you say if a diffeomorphism is isotopic to the identity, I want to ignore it. So kind of you want to look at the connected components of the diffeomorphisms. So the mapping class group, either you can define it through diffeomorphism, or you can go to the topology and define it through homeomorphisms. But these are theorems that they are in fact the same. So the mapping class group of sigma, yeah, so the official definition is okay. So, but I'm going to give you also an algebraic treatment, but I'm using a theorem, of course. It's not the diffeomorphisms of this, but only the orientation preserving one. And then I mod out by the relation that if they are the same up to isotopy, then I identify them. Or alternatively, I can say I'm modding out by the connected component of the identity. Okay, so this is the mapping class group. But let's have a better understanding of this, and that's the result. So if I give you any homeomorphism of a variety, so it's going to, if the homeomorphism is a marked homeomorphism, it's going to give you an automorphism of pi1. So now if it's not a marked homomorphism, it's going to give you up to conjugation an automorphism. So this means it gives you an outer automorphism of your pi1. And what Dan, Nielsen, and Baer showed is that so the mapping class group is isomorphic to, so when I have punctures, I have to be slightly more careful. So when there is no puncture, it's on the nose, a group of outer automorphisms of pi1. When I do have punctures, I have to permute conjugacy classes of the punctures. Okay, so it consists of those outer automorphisms of the fundamental group such that theta permutes the conjugacy classes of CIs. Okay, so in order to capture this, I'm going to lift it to the group of automorphisms as well. One thing. The other thing is okay, this is just a permutation. So I assume I go to a finite index subgroup. I assume that I do not permute them at all. I refer to that as the pure mapping class group. Okay, so the pure mapping class group consists of those automorphisms that fix the conjugacy classes of the boundary curves. And I'm going to denote that by gamma sub g comma n. So gamma sub g comma n, it's called, I'm going to refer to that as the pure mapping class group. And it fixes conjugacy classes of CIs. Okay, so, and I look at the lift of that and I refer to that as pure automorphism group. But here, it's not a good notation, I know, but nevertheless, I'm going to use it. Why it's not a good notation? Because when I put it like this, it seems that this is, I'm giving you this group and then giving you this. I'm not just giving you this group, I'm also giving you the generating set of the group. At the end of the day, this is a free group. So it doesn't have a good meaning to say, so I'm giving you the free group with the n conjugacy classes, and then this is the set of automorphisms. That theta of the conjugacy classes of Ci is the conjugacy class of Ci. And I refer to this set as the pure automorphism groups. Okay, so now what is kind of clear is that if I give you a representation, rho, then, so what does that mean? This means that rho is a representation from pi to SL to R. Now I can precompose it with any automorphism. So therefore, the group of automorphisms acts on this scheme. And one can see that it is in fact an automorphism of this scheme. Now, so this acts on that. And the pure mapping class group doesn't act on the representation variety, but it acts on the outer automorphisms, act on representations. If I look at it modulo conjugation by SL2. So that means it does act on the character variety. It does fix traces. So therefore, it acts on the character variety. So we have this kind of picture that the pure automorphism group acts on the representation variety. And then I have a map that goes to the pure mapping class group, and this acts on the character variety. And these maps are equivariant. They are compatible with each other. Okay, and now one thing that's kind of clear is that when I do this action, I'm not changing the image. So that means that if the image is irreducible, it stays irreducible. If the image is Zariski-dense, as I will describe later, it stays Zariski-dense. So if I impose certain conditions on the image, it will stay with the same type of condition. So this means that this action does not change this type of algebraic properties of the image. So in particular, this action also acts on this this open subscheme. Okay, so the next thing that I said, as I pointed out, this Zariski density is going to be preserved. So I'm going, in fact, what we do, we define, and I'm not going to define it here, but I tell you that there exists an open subscheme of the CGN cross with the following properties that's supposed to give us sufficiently Zariski-dense representations. So we show they exist. So these and this. Both of them are open subschemes. And so this goes there via the pi that we have. And so what is the main property of this thing? So the property is this. So if I give you a unital commutative ring, then I tell you that a representation from this group to SL2R is sufficiently, I'm borrowing this word from Larson and Pink. So sufficiently Zariski-dense if for any prime ideal that you pick over here, then you are going to look at the residual field, tensor it with that. Now, if the residual field is of characteristic 0, you ask to be Zariski-dense. If it is of characteristic P, you ask either Zariski-dense or it contains a copy of SL2FP. Okay, so if it is like that, then we say it's sufficiently Zariski-dense. So if so, for every n spec R, so when you look at, so when you combine it and mod it out by n, so view it as a subset of SL2, and this is the residual field over M, and you take the Zariski closure and the algebraic closure. So if the following holds, that if the characteristic is 0, it should be Zariski-dense. If the characteristic is P, then it's either Zariski-dense or it contains, so this contains a copy of SL2FP. Now, if the ring that I start with is a Z bracket 1/30 algebra, so I have to exclude these small primes, then the R points of this scheme are precisely these representations. A group that's isomorphic. Okay, so now again, the proposition is that if R is a Z joint with 1/30 algebra, then this scheme has this property that rho belongs to this if and only if rho is sufficiently Zariski-dense. And what is nice is that, I mean, we can define this one and you can detect it already there. You don't need to, I mean, so it's not surprising, right? If it is already there, this means that if one of the fibers is Zariski-dense, the other one is a conjugate of that, because it's already here. We know fibers over that are a conjugate of each other. So it's not surprising that conjugate of a sufficiently Zariski-dense is still sufficiently Zariski-dense and so on. Okay, and we still have surjectivity of the corresponding maps when D is a compact DVR and this type of results. R is any Z joint 1/30 algebra. Yeah, 3-0. So I want to avoid the small primes. I don't want to have those. As you well know, SL2F has these finitely many finite groups that have order at most 60, and I want to avoid them. And in order to avoid them, the way that I define this scheme, this has these relations, I want to avoid that. So I want to have an honest scheme over those. To say that the M's should not have the characteristic, but it's the same thing, right? Okay, so now what I have said is that I am interested in the action of the mapping class group on these sets, and when I'm not doing well, so it's okay. So what we have said is that it's going to preserve, if I start with a point over here, my orbit stays there. So now here are a bunch of theorems that we prove about the orbits of the mapping class group. So theorem 1. So this is at the level of Zariski topology. Suppose I start with a characteristic 0 field. I give you a point inside the character variety among the ones that are Zariski-dense. And I assume the following things. So the first thing is that I assume X is not among two exceptional families. So these two exceptional ones occur either when this X is essentially coming from 1, 2, or coming from 2, 1. So, but I'm not going to describe the exceptional ones. So this is not among these two exceptional ones over F. So these are, again, Zariski closed proper cases. In fact, there was a previous result in some of the results that I'm going to mention. In the SU2 case, there is a result by Previtt and Shia. They did not pay attention and they didn't exclude the E2. So their result is false. So they had to exclude that. So these are actually genuine exceptional cases. So X should not be there. And then what? So the orbit has to be infinite. And I will make a remark on this, that if G is positive, this condition is not needed. This condition is only needed when G is 0. So if this happens, that happens, then this orbit is Zariski-dense in the closed subscheme given by the boundary relations. I have already pointed out that the boundary conditions do not change through the orbit. So if something is plus minus 1, it stays plus minus 1, and the trace does not change. So these closed subschemes, without the plus minus 1s, people call them relative character varieties. With plus minus 1, we refer to them as modified relative character varieties. So of course, those parameters do not change. So it's going to be Zariski-dense inside. So the parameters depend on, so this epsilon refers to the ones that can be plus minus 1. And this depends, refers to the traces of the rest. So it's going to be dense here. Zariski-dense inside this. So you make a base change, Zariski-dense inside this one. So it's Zariski-dense. So it's better to say there is a unique variety that's defined over F. You go to the, you make it first, you model by the nil radical, you get the variety, and it's Zariski-dense inside that variety. So the variety is attached to this F variety. Unique F variety that has the same F point as this scheme. So if it is infinite, then I have this. And again, as I have mentioned, so in order to avoid these mysterious conditions, let me give you a list of cases where I don't need to mention these mysterious conditions. So that is, so if G is, if G is at least 3, then I do not need these conditions. Both of them are irrelevant. If G is 2 and n of x is positive, or product of these plus minuses is not -1, if G is 1 and n of x is not 2 and n of x is positive. So in these cases, we have the Zariski density. So these conditions are not needed in those cases. Okay, so that's theorem 1. Theorem 2 answers a question by Goldfeld. And corrects, gives the right version of a result of prevotential. So this is the SU2 case. So again, I start this time with a representation to SU2 with dense image. What Goldfeld did, he studied from ergodicity point of view the action of the mapping class group on this space. And say it again. Goldman. Thank you. So as Goldman proved the ergodicity, so he proved that there exists a gamma invariant measure and gamma ergodic measure on the representations that on the points of the character variety that comes from the representations of SU2. And then Previtt and Shia studied the same question from topological point of view. And then Goldman asked the same question. So Previtt and Shia, the result says what happens when G is positive. And as I mentioned, it's not quite correct. So there are some exceptional cases that they had to avoid. And Goldman asked what happens when G is 0. And here we give this result that again, if I avoid this and it is the image, the orbit is infinite, then it is in fact dense and where it is supposed to be. So again, under the same conditions, and you can replace them by that without no condition. So again, similar result, but this time density, similar result. But this time density in terms of the Archimedean topology. Dense in the corresponding modified relative character variety. And theorem 3 is the p-adic version. So if I give you a point, so the p-adic version says, so it says, so there are two versions of it. Let me first start with this version. So if x is inside this, then the orbit, the closure of the orbit is open in the corresponding modified relative character variety. In the corresponding relative character variety in the p-adic topology. Now, one thing that we have to so notice that this is n of x itself is an algebraic relation. So if I exclude the smaller n's, then we get the next theorem, stability result in the p-adic case. So what does it say? It says, so if I use this decoration, so the epsilons are fixed, this k vector is fixed, and when I drop h, it means I'm demanding only look at the x's where n of x is precisely n. So I do not have, so there is no so these k's might be 2, then a priori you can have identity for that point for that boundary curve as well. We want to exclude that. So then, so this consists of finitely many orbit closures. But for this one, I need to assume that G is positive. So this consists of finitely many orbit closures, and this implies a stability on the p to the k tower. So if I ask how many orbits it has in Z mod p to the kz, so the number of orbits stabilizes as k goes to infinity. So the number of gamma orbits stabilizes. Let me finish by saying one thing connected to Markov triples, as it was mentioned in Alex's talk. So the special case of this is, I didn't, this, so maybe this is exactly what I needed. So if I look at this one, so this means that I'm asking for my boundary curve to have trace T, and the boundary curve in the 1, 1 is just trace of the commutator, which I just erased. So if I put -2 here, that becomes exactly the Markov triple relation. Okay, and this decoration over here tells me that I have to subtract the trivial solution, minus 0, 0, 0 as a scheme. And so now what Bourgain, Gamwood, and Sarnak asked about the action of the automorphisms that Alex Kontorovich was mentioning is exactly asking that the action of the mapping class group is acting transitive on the FP points of this. So again, it's about the orbit closure, so to speak. So they ask whether or not the orbit is, the whole thing is a single orbit. Now what I'm saying is that, okay, so here, the orbits, in fact, there are finitely many of them, all of them are fat. All of them of order p to the kd, where d is the dimension of this scheme. So maybe it's a good place to stop.
Thanks. Is there a adelic version of this? So can you look at the closure in the
No,
adelics?
so the way that we prove it is, we use den twists, of course. So to any den twist, assuming that in my representation, the curve that I want to twist about is of infinite order, then I can, and when it is in a compact analytic one, I can attach a one flow to this thing. So this one flow has this property that the powers of the den twist are going to be dense inside this one flow. So in particular, if I'm going to end up getting an analytic curve in the closure of my mapping class group orbit. So this is quite local, right? So I'm using, and so then a technical result that's quite substantial is to find a family of, to find an expanse decomposition and linking curves. And then we apply these analytic maps one after another to these curves that we get. And we show a type of open function theorem. So we show that the differential of this is a full rank. And so that's how we get this openness. And this is done kind of uniformly for p-adic and real. And then in the real case, we already know ergodicity. So when it is open, then it's the entire thing. So we get density. But in the p-adic case, we get this openness.
Okay, but would you conjecture that there would be some kind of open image theorem?
So that I don't know. But so here I said that there is this stability. So this means from some point on, it's going to be constant. I believe that should be true. But this proof just gives existence.
Are there natural projective closures of these character varieties?
Natural projective closures.
I mean, color Shalen theory, right?
Right. I do not know. That's the honest answer.
Oh, okay.
I can imagine, but I do not know.
I mean, points at infinity are really useful.
So the point is, in this type of thing that I have studied, it was crucial to think about it as a scheme, because I wanted to work with Z mod P to the K, Z, p-adic, and all of them at the same time. But what you are asking is more about complex numbers and then compactifying it as a variety, right?
Yeah, I was really just thinking about color scaling theory, right? I mean, that's very useful for getting incompressible surfaces and hyperbolic manifolds. So,
Yeah, but I do not know.
If you replace ZP with QP, it's a genuinely bigger thing,
Ah,
right?
it's much harder. I don't know. So we genuinely worked with and used the fact that it's compact.
Right.
So it's a very good question. So I do not know this. Do we have a Teichmuller part of it? Maybe Benoit knows. I don't know. I do not know. The compactness was crucial for us. In fact, I mean, the whole thing was started long ago, maybe in 2014, 15. I was in MSRI, and then the work of Burgan-Gambo Sarnak came out for mod P. And then I worked out this in the Markov triple case. But then when I was visiting Peter Sarnak, his student Wang had results over ring of integers. That kind of pushed me to study these things.
Good.